In this video we're going to be considering some further trigonometric identities called the angle sum and angle difference identities, and then some other identities which flow on from those called the double angle identities. So what are these identities? Well, here they are, and hopefully you can see from those straight away why they might be called the angle sum and angle difference identities, because in each of these cases we're dealing with the sine or cosine of an angle which we can express as a sum or difference of two other angles. Now in this video we're going to focus on how these can be useful rather than on proving them. I'll do a proof in another video so you can watch that if you're interested. But I want you to notice straight away that these are all related to each other, and that in fact if we knew, or if we could prove even one of these identities, then we would be able to show the others just by using things that we already know about cos and sine and their relationship. So for example, let me give you an example. This last one here, I've got the cos of A take B and its relationship to this. Well, I could prove or show the second last one, the third one here, just by replacing this b with a minus b. So if I went cos of A take away negative b, which is in fact the same as cos of A plus b, isn't it? But if I use this final identity here, and wherever I see a b, because it's cos of A minus b, but I'm doing cos of A take negative b, so wherever I see a b here, sub in a negative b, and I'll be able to show that I in fact get the one before that. And likewise with these first two, I could use my understanding of the relationship between cos and sine. So again, I might show that in another video where we consider the proof of these identities. So this video we're going to focus on how we actually make use of these. Let's put a box around those. So they are our angle sum and angle difference formulas, or identities rather. And if you wanted to just check that they do in fact exist on the formula sheet, there they are, second lot down from the top, the angle sum and angle difference identities. And what I want to show before we sort of see how we might use these, I just want to show how these next one, the double angle identities, can be gained from these. So if these are true, then these ones here, the double angle identities, will flow on from that. So let's go double angle identities as well. Double angle identities. So let's start with considering the sine of the angle 2 times A. And if we looked at our first identity here for sine of A plus B, and we said let's let both A and B be equal to A, then basically over here we'd be replacing, well, A would still be A, but B would also be A. So we'd have sine A times cos A plus cos A times sine A. And really that's just two lots of sine A cos A. Alright, so two lots of that combination there of sine A and cos A. So that's the first double angle identity which relates to sine of 2A. So what we're trying to do is be able to express sine of this double angle in terms of those single angles A. Likewise, if we took cos of 2A, and so using this one here, cos of A plus B, we could say cos of 2A is cos of A plus A, so we'd have cos A times cos A, which is really cos squared A, minus sine A times sine A, which is sine squared A. So we'd have cos squared A minus sine squared A. So there's one way that we could express cos 2A in terms of just cos A and sine A. But with that one there, because of our Pythagorean identity, we could actually use that either with cos squared A to express it in terms of sine squared A, or express sine squared A in terms of cos squared A. So with both of those we could actually come up with an expression that only involves sine A or cos A, or squares of those. So we could either get 1 minus 2 lots of sine squared A, or we could get 2 lots of cos squared A minus 1. You might like to take a moment to see whether you can do that just by using your Pythagorean identity there. So this is our double angle identities, and again these ones are there on our formula sheet. You can see those ones there, our double angle identities. So all of those are given to us and we don't need to be able to remember them. So let's maybe have a quick look at some ways in which we might actually use these. So let's consider if we were trying to evaluate something sort of tech-free. So let's grab a couple of questions from the exercise. So what have we got? Question 1, let's start with A. We've got cos of 165. Now 165 is not something that we can do using our current exact values. In other words, it's not a multiple of 30 or 45 or 60 or even 90 degrees. But we could express it as the sum or difference. So 165, what could we express that as? We could say 120 degrees plus 45 degrees. So if we express it that way, then now using our cos A plus B, so our angle sum identity, which involves cosine, we can now express this using this right hand side here. So what do we have? We'll have cos of 120 times cos of 45 minus sine of 120 times sine of 45. And now we sort of need to remember our exact values, including exact values of cos and sine in other quadrants. So cos of 120, well, cos is definitely negative in quadrant 2, and for 120, cosine is the same as 60, so that's a half. Then cos of 45, well, that's just root 2 over 2, minus sine of 120, sine is positive in quadrant 2, and sine of 120 is the same as sine of 60, so root 3 over 2 is its sine, and sine of 45 is, again, root 2 over 2. So what do we get when we simplify that? We'd get negative root 2 over 4 minus root 6 over 4. So we could sort of leave it like that, or if we wanted to, I guess we could express it as kind of a single fraction, root 2 minus root 6 over 4. So there's one way that we can use our angle sum and angle difference identities, is to get exact values for in situations where we don't actually have exact values presently. So let's do another one. Maybe let's do one using radian measure. So what have we got here? Question 2. Let's look at B. So we've got sine of 11 pi over 12. Now there's a couple of ways you might do this to sort of simplify it or understand it. One is that you might try and think of your angle in degree measure rather than radian measure. So when you're thinking about 11 pi over 12 and you're trying to work out what can I add or subtract to get 11 pi on 12, you might, like I say, think of that in angle measure. Alternatively, one way that it might help you to express 11 pi on 12 using angles that we are familiar with is just to actually think about so things like pi on 6, pi on 4, the angles that we do know the exact value of cos and sine for, and express each of those using that denominator, which in this question is 12. So pi on 6 would be 2 pi on 12. Pi on 4, what's that? 3 pi on 12. And pi on 3 would be 4 pi on 12. So basically, if we can express 11 pi on 12 using multiples of these ones, then we should know the exact values of those. And there'll be different ways that we can do this. So I could see, for example, that we could use these two here by saying it's 3 lots of this one. That'd be 9 pi on 12 plus 2 pi on 12. So if I said that that was equal to sine of 9 pi on 12 plus 2 pi on 12, because that is sine of, what's that, 3 pi on 4 plus pi on 6. Now, because I do know exact values for sine and cos of those angles there, I can now use this first angle sum identity here to rewrite my expression in terms of sine and cos. So what have I got? I've got sine of 3 pi on 4 times cos of pi on 6 plus cos of 3 pi on 4 times sine pi on 6. So what's that equal to? Well, sine of 3 pi on 4, so that's in quadrant 2, and 3 pi on 4 is the same as has the same magnitude as sine of pi on 4, which is root 2 over 2. Cos of pi on 6 is root 3 over 2. Cos of 3 pi on 4 is negative root 2 over 2, and sine of pi on 6 is a half. So pretty important with these that we know our exact values. So what's that? Root 6 over 4, and that's going to be minus root 2 over 4. Root 6 minus root 2 over 4. Alright, so there's a couple of examples of how we can use our angle sum and angle difference identities.